There's this word again, amphoteric. Water can act as an acid or a base. And what's crazy about it is it does this even with itself. You know, two water molecules together, and one can donate a proton to the other, forming hydronium ion and hydroxide ion. And you might say, well, why on earth would they do that? Well, they don't do it very often. You could almost think of it as kind of a mistake. You know, they do it by accident. And, oh, hey, wait a minute. Why did we do that? Let's give me that back. It happens little teeny, tiny bit. It's called self-ionization. So it's ionizing with itself. Happens very, very little, but it does happen, and it's important. Small extent. Now, we learned about, we've already learned about equilibrium constants and their expressions. So if we think about this equation, H2O liquid plus H2O liquid in equilibrium with hydronium, which I guess we would have to say is aqueous, and hydroxide, which is aqueous. We learned how to write an equilibrium constant expression for that, didn't we? You take the concentrations of the products multiplied by each other. If there's coefficients, you do the whole exponent thing, divided by the concentrations of the reactants. But these are both liquid, right? Liquids and solids don't change their concentration, so we leave them out. So down here, let me circle that. This is the equilibrium expression for that self-ionization of water. There's K, the equilibrium constant. They call it the ion product constant, KW. It's just the equilibrium constant for the self-ionization of water. It's the concentration of hydronium ion times the concentration of hydroxide ion. And it's a constant. It's always 1.0 times 10 to the minus 14. And they determined that experimentally. It seems like kind of a nice roundish number, but it is what it is. Not all the numbers that we find are crazy complicated numbers. So when we look at this, when this occurs, we must have equal amounts of hydronium ion and hydroxide ion, right? Because they came about at the same time. This was created by one water molecule accepting a proton from another, which created this simultaneously. So those have to be equal, right? If those are equal, they're going to be each 10 to the minus 7th molar, because 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7 is this constant, okay? So is that a large concentration? 0.000001 moles per liter. Very, very small. Water is actually 55 moles per liter. So it's a really, really small amount of water that is doing that at any one time. But that's what happens to pure water. And so we call that a neutral solution. And all of these solutions we're talking about are aqueous. They have water as the solvent. So a neutral solution will have the hydronium ion concentration equal to the hydroxide ion concentration. That's what we call neutral. Acidic means maybe we added acid to it, right? Acid it donates hydrogen ions. The water will accept it. It'll cause the hydronium ion concentration to go up. So if the hydronium ion concentration is higher, then it's an acidic solution. And these are inversely related. So there's a pulley and here's a rope going over the pulley. If I pull down on this end of the rope, the other end of the rope goes up. I can't make both ends come down at the same time. If one goes up, the other goes down. That's just how it works. And that's how these concentrations work. If this one goes up, if this one gets bigger, that one gets smaller. So acidic solution has the hydrogen ion concentration greater. Basic solution has the hydroxide ion concentration greater than in a neutral solution. And this is the general equation. And so this is hydronium ion times hydroxide ion. If one gets bigger, one has to get smaller because they always multiplied together equal the same number. So this helps to see how they are interdependent. Here we have hydronium ion concentration in pure water. It's 10 to the minus 7. If we increase the hydrogen ion concentration, it becomes an acidic solution. And at the same time, the hydroxide ion concentration is going down. If we increase the hydroxide ion concentration, it's a basic solution, and the hydronium ion concentration is going up. Let's just look at, well, that's not what I meant to do. Let's just look at one combination here. Let's look at these two. So if the hydronium ion concentration is 10 to the minus 10, the hydroxide ion concentration is 10 to the minus 4. And if you understand multiplying exponents, you can do that one in your head. It's 10 to the minus 14. Or you can pull your calculator out and prove that it's right. So these are related because whatever number this is times that number always gives us 10 to the minus 14. So let's do this one. I'm actually going to start with the one on the bottom, just because. So it's asking us to calculate the hydronium ion concentration and then determine whether the solution is acidic, basic, or neutral. So let's look at C first. Hydroxide ion concentration is 8.2 times 10 to the minus 10. To find the hydronium ion concentration, we need to use that equation. Hydronium ion times hydroxide ion equals what? (1.0) times 10 to the minus 14. We know the hydroxide ion. We just need to rearrange this equation and solve for hydronium ion. So we'll divide by hydroxide on that side, and we'll divide by hydroxide on this side. Those cancel out. So this is very much like what we did in chapter 15. In fact, it's exactly the same thing. So 1 times 10 to the minus 14 divided by 8.2 times 10 to the minus 10. Now, you just need to be careful that you're using your calculator and scientific notation correctly, otherwise you will get the wrong answer. So 1 EE minus 14 divided by 8.2 EE minus 10. I'm getting 1.2 times 10 to the minus 5. That's the hydronium ion concentration. Any questions? And then I overlooked this morning. And determine whether the solution is acidic, basic, or neutral. Well, how do we do that? We compare the concentrations to neutral, which is 10 to the minus 7. So here, 10 to the minus 5, is that a larger concentration or a smaller concentration than 10 to the minus 7? It's larger. So the hydronium ion concentration is higher. Hydronium is acid. So this is acidic. B, we can actually do without doing any math. It's neutral, because the hydroxide is 10 to the minus 7. And if the hydroxide is 10 to the minus 7, then what's the hydronium ion concentration? It's the same. And then the first one, Is that acidic or basic? It's basic, right? So I'm looking at the hydroxide ion concentration. This is larger than 10 to the minus 7, which would be neutral. More base means it's basic. The hydronium ion concentration would be Kw, which is 10 to the minus 14, divided by the hydroxide. .3 times 10 to the minus 13. So make sure that you and your calculator are communicating correctly.